Doctor, you're rolling. You may proceed.
Yes, good afternoon. We are discussing, if you remember, I will just remind you again, free vibrations of simply supported beam. So this is this beam of length L. So let me write down free vibrations of a beam that is simply supported. At its both ends. Some governing differential equation is EI d4w dx in force power plus rho a d2w dt squared is equals to 0. And we said that small wx of t is represented in the form of capital W of x in power I omega t, or maybe cosine omega t. So this is W, and this is omega, because these are different things. This is a function of x, and this is a natural frequency. We are looking for. Okay? So what we did, we substituted this there. It is nice to write all of this again. So then it will be d4 capital W dx in force power. We substitute this into here. And then times cosine omega t. Then plus, okay? Or minus, because second derivative of cosine omega t will be minus omega square rho a, and then will be capital W, and then derivative will be cosine omega t. This equals to 0. And we can take out cosine omega t outside parentheses, and what is left then will be EI d4 capital W dx in force power minus rho a omega square capital W equals to 0. Now this differential equation, this equation should be valid for all t's. So therefore, we can write down this governing differential equation as follows. EI d4 capital W force derivative minus rho a omega square capital W equals 0. Then we divide by EI. And we got d4w dx in force power minus rho a omega square over EI capital W equals 0. Then, because we have this force derivative, it makes sense this expression to be called alpha in force power. Okay? Because when I differentiate expressions that I will need, I will get, so I got then W force derivative minus alpha in force power, capital W equals 0, and this alpha in force power equals rho a omega square EI. So that was our notation. Okay? Then we actually solved this W from this differential equation, W of x. And solutions, this I'm not going to repeat here. We wrote down like A1, I think. What were the coefficients? Okay. A1 K1 alpha x plus A2 K2 alpha x plus A3 K3 alpha x plus A4 K4 alpha x, and these K functions, Kj of alpha x, these are Krylov functions. And actually, I asked you past time to write down these functions separately on a separate sheet of paper. And actually, I give you a copy in case you forgot to bring. Those who are taking this course by feet or over distance learning, I cannot give you a sheet of paper, but I hope that you wrote already for yourselves. And you have these functions with you. And when then we engaged in solving this, so this W of x is called mode shape. Mode shape means shape that this beam takes while it vibrates. What kind of shape it has? This beam is vibrating, so it has an amplitude, some maximum, minimum, etc. So what is the shape of this beam? Beam naturally does not stay straight. Had it stayed straight, then it would be not vibrating. It cannot possibly stay straight because there are 2 points that are connected to zero, so displacements are zero. So had it been staying straight, then everywhere displacement would be zero. But then we would not need all this analysis. We were looking for the solution where W of x is not zero everywhere. So we wanted W alpha x is not zero everywhere. Then I will very fast go through what we did. And we said a beam simply supported at its ends, W equals 0, second derivative equals 0 at x equals 0. The same conditions hold when x equals L. Okay, then what we did is as follows. These K functions have very nice property. K1 at 0 equals 1, but K2, K3, and K4 at 0 equals 0. So when I substitute here 0, I want to evaluate W at 0 equals 0. Then these expressions are falling down because K functions are taking value 0, and we are left with A1, K1. But K1 at 0 equals 1. You may look at this function, and you see that A1 at 0 equals 1, because it's hyperbolic cosine plus hyperbolic cosine and just regular cosine. So therefore A1 equals 0. We showed that because of second derivative A3 equals 0. So we were left with these two things only, A2, K2, A4, K4. Then we demanded conditions at L. So this is displacement equals 0, A2, K2, A4, K4 equals 0. Okay, because this and this fell out. Now here, when I differentiate this K2, so we may also write down, these forms that we did, if you remember. Okay, so we can write down here on this page K1x, then K4x, K3x, and K2x. Okay, derivative of K1 is K4, derivative of K4 is K3, derivative of K3 is K2, derivative of K2 equals K1. Or actually, d Km of x dx equals Km minus 1. And when I differentiate K1, so K1 then I get one number less, which is 0. K0 at x is identified as K4 of x. Okay, so we may hold this page. So therefore, when I differentiate K2 once, I get K1. When I differentiate it once more, I get one less, which is K0, which equals K4. Here, when I differentiate K4, I get K3. Differentiate once, get K2. So I got this expression. And then I demanded that this determinant, which is a determinant for the for A2 and A4. A2 and A4. I'm looking for A2 and A4 because if I know A2 and A4, then I know the mode shape. Okay. So I got this determinant K. So that is this expression that I got. K2 alpha L, K4 alpha L, K4 alpha L, K2 alpha L. And I got this expression. K2 this times this minus this times this. K2 squared minus K4 squared. So all of these we had. Then I substituted here K2 and K4. And we had this expression. 1/2 hyperbolic sine plus trigonometric sine plus hyperbolic sine minus sine and squares. And we got sine alpha L equals 0. That means that alpha L equals K pi. K is an, by the way, we could write here that K could be 0 also naturally. If K equals 0, this is okay. This expression is okay. But if K equals 0, then alpha equals 0. Alpha equals 0 corresponds to 0 natural frequency. But one can show that 0 natural frequency is not possible in this case. So alpha L equals K pi. K equals 1, 2, etc. So then we substitute in this expression. So today I repeated this. Rho A omega square over A equals alpha in fourth power. I substitute this omega square. In omega square, I substitute the alpha expression. Alpha equals, pay attention, K pi over L. I got this expression finally. Omega squared equals EI over Rho A, K pi over L in fourth power. And that is omega K squared. Omega K squared. So we found that this beam has infinite amount of natural frequencies because K runs values 1, 2, etc. Okay, now what we get is as follows. Now we found already these frequencies. Now let us repeat, how did we find these frequencies? How did we find the frequencies? From the expression, I think A2K2 alpha L plus A4K4 alpha L equals 0. Then we had A2K4 alpha L plus A4K2 alpha L equals 0. So this is from set. From this set we got. I just recall you, where did we get this natural frequency from? Okay. Okay, now we found alpha. Alpha L, okay? Alpha L equals K pi. Now, since we found, so let us put it back. Put back. So we find A2K2 and alpha L, yeah? So that is K pi, yeah, we have a K pi plus A4K4 of K pi. So that is small k, of course, yes? Equals 0. then A2 K2 K pi and plus A4 capital K2 of K pi equals 0. So determinant equals 0. We found alpha L from the demand that the determinant equals 0. But because determinant equals 0, these two equations are dependent. Okay, for just as an example, as in the following example. Say 2x1 plus 7x2 equals, say, 15. And then 4x1 plus 14x2 equals 30. So these equations are dependent because second equation equals first equation times 2. And indeed, just check the determinant. 2, 7, 4, 14. That equals 2 times 14 is 28, minus 4 times 7 is 28, and this guy is 0. Just brought an example, simple example for illustration. Okay? Now, these two equations are dependent. Because they are dependent, since they are dependent, we don't need them both. Why? Because they provide the same information. Okay, like here. Look, this equation is the same information like here, just it's multiplied by 2. So once I divide it by 2, I will get the same thing. So I don't have to write it 2 times. It's the same thing. It's the same information. So therefore, I must write just one is enough. One equation is sufficient. Okay, so one equation is sufficient. Therefore, I will take the first equation. We take the first equation, which is what? A2 K2 alpha L plus A4 K4 alpha L equals 0. So from here, we can get, look please, now we have just one equation with two unknowns. A2 and A4. So we have infinite amount of solutions, one equation with two unknowns. And we can express actually A4. Now I think you did not have this. And a few minutes we are already in a new topic. I just repeated because we have a new person. But now we will go further. So A4 then equals minus K2 over K4 times A2. So that means that actually we can determine everything up till some coefficient A2. So A4 then equals minus K2 over K4 A2. And now we can actually substitute here. Let us calculate now these values, K2 and K4. So alpha L K's value equals K pi. So we substitute now here. K2 alpha L. So it turns out that K2 and K4 alpha L equals both hyperbolic sine divided by 2. Why? Because sine function vanishes. Look, in K2, we have hyperbolic sine plus sine alpha x. The sine alpha, that is in K2, I have plus sine. In K4, I have minus sine. Plus, minus. But when I substitute here instead of xl, and then this alpha l equals k times pi, sine function of k pi equals 0. So therefore, these two things are equal to each other. So therefore, k2 alpha l and k4 alpha l equals just hyperbolic sine divided by 2 alpha l case value. So they are equal to each other, k2 and k4. Because they're equal, then here I have just 1. This value, please circle, this value equals 1. So a4 actually equals minus a2. a4 equals minus a2. So we are looking for the mode shape. Hence, w of x equals a2 k2 alpha x plus a4 k4 alpha x. Now a4, as I said, equals minus a2, so I can take out a2. So we will have k2 minus k4 alpha x. You want me to put down? Fine. So then if you compare sine functions, if you compare actually k functions, then k2 minus k4 equals sine function. So the mode shape is interesting. It is actually sine function. Who is Major Silampa? Then Flores is not here. Mr. Peguero, he is not here. Do I pronounce your last name correctly? Silenpa, okay. I think this is you. There is not here. Yes, so what happens is that mode shape equals a2 times sine alpha x. Now, what is the conclusion? First of all, one conclusion is that mode shapes are depending upon some constant, a2, which is not determined. We did not determine, we solved everything. We found actually natural frequencies. There are infinite amount of them. Mode shape is not determinable uniquely, which is understandable, as we know from eigenvalue problems. And now we have this function. So that means that there is a shape. That is why it is called mode shape. It is not called mode function, but it gives us only a shape. Shape is sinusoidal shape. So, but how much this value will be depends upon initial conditions or initial kick we impact or impart on the system. So please write down that mode shapes are determinable up to a constant, a2. a2 stays undetermined. we will need, so to say, initial conditions, etc., to have them. Now let us see what is this sine alpha x. We know what alpha is. We found this alpha. This alpha, of course, equals alpha L equals k pi. So therefore, alpha equals k pi over L. K is a positive integer. So I substitute this alpha over there, and I get k pi x over L. So we can actually say that if I take A2 equals 1, then shape is sinusoidal shape sine k pi x over L, or W of x equals A2 phi or phi k sub x. So this is mode shape, as we said. Now let us look how this mode shape looks around the beam itself. Okay, when k equals 1, the shape is like the sinusoidal. So these are the ends. Ends are connected, so displacements are 0. So this is 1/2 wave of sine function. Please write it down. 1/2 wave of sine function. That is a first mode shape. Now, second mode shape is 2/2 sine waves. So what is k? K is number of half sine waves in x direction. Remember, we got everything is alpha L equals k times pi. So this k is not just positive integer. It signifies something very important, this k. It signifies number of sine half waves in x direction. Okay, any questions, any discussion? So actually this problem has been, so to say, dealt with. We found mode shapes. We found infinite amount of natural frequencies. So first natural, so what is this? What does first mode shape says? First mode shape says that this mode shape corresponds to first frequency. So when system vibrates at the first frequency, it vibrates like this. When it vibrates with second frequency, then it vibrates in this shape. When it vibrates with the third frequency, then it has 3 half sine waves, etc. So actually we are getting that this system actually can vibrate in any of these forms, depending upon what is realized in the experiment. It can do any of these things. Okay, so it's like a multitasked servant, if you want, like a robot which could do one of the many, many things, if we can look like that. Yes, sir? With what? Yes, this beam is vibrate. Student asked, I must repeat for those who are taking it in distance. Student asked whether we are dealing with the plane system. Yes, this beam vibrates in the plane of this sheet of paper. In the plane, does not vibrate out of plane, not in space, but in the plane. It's the simplest possible case. Any other questions, please? Okay. Say it again? Yeah, the question was whether or not there is a model where beam vibrates in space. Yes, naturally. There is such a model. Yes. For example, helicopter vibrations are associated with something that takes in space, and therefore we should have vibrations, say, in X direction, in Y direction, in Z direction, and then interrelatedness between these vibrations, etc. Yes, the answer is yes. Any other questions? This is the simplest possible case of beam vibrations. But even in the simplest possible case, we found infinite amount of natural frequencies. Okay, so we said that alpha equals k pi over L. They are roots of transcendental equation. So then alpha equals what? K pi over L, so it's pi over L, or 2 pi over L, 3 pi over L, etc. It has infinite number of solutions. Countable infinity. We can count 1 times pi, 2 times pi, 3 times pi, etc. So these values, alpha, are also called eigenvalues. Let me write it down here. Alpha, eigenvalues. So eigen is a German word. And values is an English word. So somehow they appear in the same word. So every time you type it in the computer says that it does not feel very comfortable with this. Okay? So eigen actually means own. Okay? For example, Eigenschaft means property or own characteristic. Okay, so it comes from this word eigen, German word. So these eigenvalues are used also in English literature on both sides of Atlantic. So a continuous structure that has infinite degrees of freedom has infinite number of eigenvalues. So in the very beginning, if you remember, of this course, we did have this cantilever beam with the mass at the end. And we found dynamic natural frequency via static analysis, if you remember. And that, what we did there, was we find that our consideration of a beam is a 1 degree of freedom system was an approximation. What we did in the very, very beginning, first or second lecture, was an approximation. What we did with static approximation of dynamic problem was an approximation. In reality, there are infinite amount of natural frequencies. Just one small thing that will finish this small chapter is as follows. Why the beam has infinite degrees of freedom? So you did not ask me this question. Why does the beam have an infinite amount of degrees of freedom? Yes, please. You want to comment or to ask? Or to respond? Okay. Can you speak louder? The beam. So, and you think that 6 is infinite. Student says that beam has 6 degrees of freedom. But I said that the question is, why does it have infinite degrees of freedom? Or you think that 6 is a lot, so it's 6 is infinity, or what do you mean? Okay, so I understand what you're saying. Okay. So what student says that maybe what he means is that he actually disagrees with the statement that not disagrees, but he thinks that maybe beam has 6 degrees of freedom system corresponding, as he says, 3 directions of movement and possibly 3 rotations. No. Let us look at the beam. So we are interested, we want to find the number of degrees of freedom. Now what is this? This is a minimum number of coordinates to be able to describe in a unique manner the position of the beam of the, say, points on the beam. When I say beam, I mean points of it. So now how many points are here? There are infinite number of points between 0 to L. Now in order to find the location, we actually have to say where beam is here, in this point, and in this point, and in this point, and at this point. So we need actually to give a function, whole function. So I will want to know the positions at infinite number of points of the beam. So because this W of x between x belonging from 0 to L, there are infinite number of points, and I need to know the values. So W at 1 point, 2nd point, 3rd point, etc., infinite number of points, means that I need actually infinite information or infinite number of information in order to say where the beam's points are. So that is what is meant by infinite degrees of freedom. That is what. Now, let us talk about approximations. Let us say about approximations. Okay? Let us talk not, this was transverse vibrations. Do you remember transverse? So that is perpendicular to this axis. But if we talk about longitudinal vibration of the bar, then we have like this. Say imagine this is connected and this is connected, say. Then I actually, and vibrations are in x direction. So I need actually where this point is moving and where this point is moving, where this point is moving, where this point, so many, many, many points. So this is actually equivalent to have here 1 degree and here 1 degree of freedom, this mass. So imagine I'm cutting this and I'm lumping the masses. Okay, so this mass is here, M1. This mass is here, M2. This mass is here, M3, etc. And then there should be some springs there, springs attached. So actually I'm getting that this beam is equivalent to this mass and spring. And this mass and spring. This mass and spring, etc. So we need actually infinite number of masses and infinite number of strings in order to represent this beam. This is how actually historically the vibration equation was obtained. Frenchman Lagrange obtained from these considerations, okay, from infinite number of system, he obtained equation for the longitudinal vibration of the bar. Yes, go ahead. Can you speak louder? Yes, but in our particular case, this infinity of degrees is now lumped in one function. Once I know the function W1, W2, W3, etc., then I know, I mean, do you remember we wrote, let me put here. So we had first shape is like this. Second shape, so is like this. Third shape then is like this, etc. So in each case we have, so in order to depict the behavior of the system, we are also getting, because we have infinite degrees of freedom, we get infinite amount of mode shapes. So this is phi1, or if you want W1, phi2 or W2, phi3, W3, etc. Any other questions or comments? Okay, say it again. Can you repeat your question? Yes, a question was asked whether this type of solution could or would lead to finite element formulation. Yes, yes. Answer is yes. Any other questions? Okay, if we have no other questions, we will go further, but I will just show you, say, this beam naturally could have shape either upwards or downwards, and actually vibrations, and if it was by first mode, would be from, so takes this form and then this form, etc., and vibrates in both directions. Homework assignment, please write down. Derive the frequency characteristic equation for the beam which is simply supported at one end and clamped at the other. Please write down. Now it also says find asymptotic expressions for the frequencies. I'll explain you what that means. Okay, show that the transcendental equation for frequencies reads. That is this. Okay. Now, please, okay, you will get the equation tangents alpha L equals hyperbolic tangents alpha L. I mean, that is what I would like you to show. Hyperbolic tangents of alpha L, of course, equals hyperbolic sine divided by hyperbolic cosine. Now, please find graphically solution of this equation. And check how close they are with these solutions that I gave you. Alpha L1 equals 393, alpha L2 equals 707, alpha L3 equals 1021, and please find the fourth one. Please find the fourth one, alpha L4. Now I would like to ask you to find it graphically. I will tell you how to find it graphically. Did we write everything? Not yet, okay. I'll wait. So I would like you to plot a figure like this. So on the same figure to plot function tangents alpha x, or tangents alpha L, or tangents x actually. So this whole thing say is x or alpha L or whatever. And so if you want just alpha L, and here we could write alpha L. Then this is pi over 2, 3 pi over 2, 5 pi over